the function f of x equals x plus 1 over x minus 3, just for reference. Excuse me, this is called a rational function. It's got a polynomial for the numerator and a polynomial for the denominator. Now, pretty simple polynomials, they're just linear, but they're going to grow as we go through the idea of rational functions and their graphs. Okay, so first of all, if we wanted to graph this thing, what's its y-intercept? Well, the y-intercept is obtained by substituting x equals 0. So y would equal f of 0, which is negative 1/3. All you got to really do is just ask yourself, if x is 0, what do you have here and what do you have here? Clearly, you've got 1 and negative 3, and that's negative 1/3. So on a graph, the graph would have to go through the point 0, negative 1/3. Now, for what x values is f of x near 0? But the only way f of x could be 0 would be for x to equal negative 1. The numerator would have to equal 0 in order to get 0. No choice. The only thing that you can divide by another number and get 0 is 0. Okay? So, and if x is close to negative 1, then you expect x plus 1 to stay fairly close to 0. And x minus 3, if x is equal to negative 1, is equal to negative 4. I had negative 2 there because I carelessly wrote down a 1 here before I put in my negative. Okay? See if I've got any other negative 4s there. Okay? Okay. So, if x is equal to 1, numerator is 0, denominator is negative 4. If x is close to 1, well, then the denominator will be close to negative 4, and f of x will still be close to 0. So the x plus 1, the numerator, will still be close to 0. So f of x is still going to be close to 0, because if you divide something close to 0 by something that's close to negative 4, you get something that's close to 0. Now, the denominator, when is the denominator 0, and what does that tell us? Well, the denominator is 0, clearly, if x equals 3. 3 minus 3 is 0. Of course, you could set x minus 3 equal to 0, add 3 to both sides, and you get x equals 3. So just by setting the denominator equal to 0, you get an equation that you can solve and find out for what x values that occurs. Well, then, if x is near 3, the denominator is close to 0, because something close to 3, if you subtract 3, you get something small, something close to 0. And the numerator is going to stay near 4, because if x is 3, the numerator is 4. If x is close to 3, you expect the numerator to still be close to 4. Okay, so we're going to say now, if your denominator is close to 0, and the numerator isn't close to 0, which is the case here, the denominator is close to 0, numerator is close to 4, then the denominator goes into the numerator lots of times. Okay? Small things go into things that aren't small lots of times. So I'm going to say small goes into not small many times. And then, we actually did a counting. I say count to 4 by 1/10. Okay? If the denominator was about 1/10 and the numerator was about 4, what would the result be? You can punch 4 divided by 0.1 into your calculator, but that doesn't tell you anything except what the answer is. It doesn't tell you why it is. It doesn't tell you how to think about what happens to this function. It only tells you what happens without giving you any insight whatsoever. So, we decide, okay, we'll count to 4 by tenths. Ready? 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, right? And then you're going to have 10/10. What's 10/10? It's 1. Now, when we did this in the FCR class, we went 0.1, 0.2 up to 0.9. So we have 0.8, 0.9, and then what? 0.10? Well, no, that's not what happens, okay? If you add 0.1 to 0.9, you're adding 1/10 to 9/10, and you get 10/10, and 10 divided by 10, that's what I mean by 10/10, is 1. Okay, so in decimals, 0.1 up to 0.9, and then we get 1. And then we get 1.1, 1.2 up to 1.9, which means same thing as 19/10, right? And next we're going to get 20/10, which is 2. And then we go from 2.1 up to 2.9 and add a tenth, we get 3. And then up to 3.9, add a tenth, we get 4. We need to understand that without having to write a lot of things out. We have to understand what it means to count by tenths in order to begin to understand what all this means. And this is something I'm afraid people just don't think about when they're in a calculator-based math curriculum. So it's very difficult then for people to understand how this function behaves, but this is very important, so we need to develop this. Okay, anyhow. So, and then, you know, when we got up to here, I said, so how many times does 0.1 go into 4? And immediately got the answer, 40. So, you know, people understood this well enough to answer the question after going through the exercise of counting. So make sure you understand how this works, and make sure you understand what would happen if you tried to count to 4 by thousandths. Okay, 1,000th, 2,000ths, yeah. You'd have to go all the way up to 999 thousandths before you got to 1. Okay? And then you'd have to do that 4 more times to get up to 4. It'd be 4,000 times, right? You don't have to have a rule that says move this decimal this many places, and if you got this many zeros, and so forth, and you don't have to have a calculator where you punch it in. You understand what it means for the denominator to be like 1,000th. If x is close enough to 3, that'll happen. And if it does, x plus 1 is going to be very close to 4, isn't it? So you're dividing 1,000th into a number that's very close to 4, you're going to get a result that's very close to 4,000. You get much closer, you can get as close to 3 as you like. You can get a billionth of a unit away from 3, meaning when you divide it in, you're going to end up with 4 billion. So there's no limit to how big these results can be as x gets close to 3. So I make the statement, as x gets closer to 3, f of x gets bigger. Okay? And how big is unlimited, because x can get as close to 3 as we might wish. You tell me how close you want to get to 3, and I'll give you a number that's closer. We can do that all day. And I can give you a number close to 3, you can give me a number closer. Okay? So, we can say now, well, to the left of 3, that means for x values less than 3, here's 3. To the left of 3, the denominator is negative. To the right of 3, the denominator is positive. The numerator stays close to 4 when you're close to 3, so the numerator stays positive. Okay, so as you get very close to 3, the denominator is negative as you move close to 3 from the left, from numbers that are to the left of 3, for numbers less than 3, 2.9, 2.99, 2.999, whatever. The denominator is negative, and it gets huge because of what happens when you divide a smaller and smaller number into a number that doesn't change much. It gets huge without limit. So what you have is a vertical line through x equals 3 and a graph that's approaching x equals 3 as an asymptote. To the right, your denominator is positive. It gets huge. And I should say, f of x gets huge without limit, just as I should have said that it's f of x that gets huge without limit here, but in a negative way. Okay, here f of x gets huge without limit as x approaches 3.